All right, today I thought we would take a look at one of the data paths that this board has. It outputs a QAM signal, a quadrature amplitude modulated signal. And so I have this hooked up. It gives you a QAM 1 value, a QAM 2 value, and a clock value, okay? So when to gate the clocks. And so we will be using channel 1, channel 2, and channel 3 on the oscilloscope for the QAM I value, the QAM Q value, and the QAM clock. Okay, most of the time these are called I and Q. You could just think of it as X and Y. You can think of it as channel 1, channel 2. But yeah, this is the I and the Q for the QAM output. So we'll come up to the oscilloscope and take a look at what these signals look like. Okay, let's talk about ones and zeros. Okay, we all know that. Digital electronics, you know, this is a 0 and that's a 1, and that's the way you transmit data, zeros and ones. What if it was nice? What if we could transmit more than a 0 or 1? What if we could transmit a byte at a time? You know, 0 to 256. Why can't we transmit a 0 to 256? Or why can't we transmit 0 to 8? Or 0 to 7, right? 0 to 7, eight values every single time. Well, we could, but it would require us to have 8 different lines, right? We only have 1 line. But what if we were a bit clever? Instead of assigning this voltage as 0 and this voltage as 1, we had a whole bunch of levels where this is a 0 and that's a 1, 2, 3, 4, 5, 6, 7, right? And so we have a way of amplitude modulating the signal that correspond to different digital values, okay? So that sounds a bit odd, but let's take a look at that. I'm going to zoom out here. What we're looking at here is this traces the clock. This is when we're going to sample the data. Okay, we're going to sample the data at these times, and this is our data. So it's taking a while for it to translate from one value to the next value. It's going to take some path to get there. But one of these values will be 0 to 7, and one of these values will be 0 to 7. And let's just do a single shot. So here's a single shot. So you can see that here we're at that value, then we're at that value, now we're down here at that value, now here we're at that value. And so we're going to sample the data. So the data is going to be zooming around, right? And so we are amplitude modulating the data into discrete levels, and then we're sampling it, all right? And then if you have completely random data, you're going to get something like this. You can sort of see that this could be any value from 0 to 7. This could be any value from 0 to 7, and that's the way we encode this. Okay. So that is amplitude modulating a digital signal. I don't know exactly what this is called, but if we do it a second time on a different channel, so now we have. Let's go down here. Oops. Okay, so now we have one channel that has the yellow information. We have one channel that has the blue information, right? And if we do a single shot, we can see that at each sample point, the yellow is going to be at one value and the blue is going to be at a different value. So the yellow can have a value from 0 to 7, and the blue can have a value from 0 to 7. Well, that's 8 and 8. Well, that's 64 different values, okay? 64 different values are encoded with just these 2 signals plus a clock, okay? And this is what's known as quadrature modulation, where you can think of it as in X and in Y, right? You're giving one X value and you're giving one Y value. You're giving one channel 1 value. You're getting one channel 2 value. Anyway, you're getting 2 values, and if you plot that in a 2-dimensional space, one of these being X and one of these being Y, you will have different locations, okay? So let's turn this back on, all right? And let's make these a little bit bigger so we can sort of see what's going on here. And yeah, so the data can just be just be anything, right? It's just going to zoom around in there. And you can see that it's taking a path to go from, maybe it starts at this value and the next time it's at this value and the next time it's at this value. So it's going to take some path, right? It's going to have to take some path. And so you're not worried about the values along the way. You're worried about the value when the clock when it appears. When the clock is here, when the clock is here, the data has to be valid, right? That's true in digital signals as well. There's some, between bytes, the bus line can be anything arbitrary. It needs to be quiet when you actually clock the data. You either have an edge clock or you have some type of high value, some type of level clock. But again, your data has to be stable when it's time to sample it. And it's no different. It's no different in this particular system. But in here, this is one way to look at the data, right? Now I talked about taking the data and assigning one value in the x direction and one value in the y direction, and we can do that on the oscilloscope. We can say acquire, and we can change it into XY mode. Okay, and when we go into XY mode, we now have one of those values in the x direction and one of those values in the y direction, and this is the type of display that you'll often see in a QAM64 or other types of modulation schemes. I believe these are called constellation diagrams. All right, so this is the display that you would normally expect to see if you're looking at a 64 QAM display. It's 8 bits in one direction and 8 bits in the other direction, and you see all those little dots here. So how do you get that on your oscilloscope, okay? And you need to go to XY mode, all right? Now, I've done something a little fancier here in XY mode, but let's first take a look at XY mode. XY mode is dependent on how fast your scope is sampling. Right now I have it sampling as very fast as it can. If I slow it down, you can see that it is kind of filling in. It's catching more events. It's almost like a persistence knob in XY mode. It's how much sampling do you do before you put the picture on the screen. So anyway, I'm just going to crank it all the way up. That seems to work really good. And so you can see that there's a couple things happening here. I'm going to explain one before, okay? I am going to first, you might first hook it up and you maybe get something that looks like this. So what you need to do is you need to set the vertical on both of your channels to get to where you want to go. Now, there are 8 of these dots across the screen, and they're not lining up on the grid of the display. And it'd be kind of nice if they lined up on the grid, that you can kind of see if there's any linearity or problem, something like that. So on digital oscilloscopes, if you press the button, instead of going in clicks of predetermined amounts, it'll go into a linear mode where you can just make it anything you want. What I'm going to do is I'm going to bring over this last dot. I'm adjusting the X, size of the X basically is what this adjustment is doing. And I'm going to keep bringing it over until I'm getting my X value right there on that line. So now I have 8 lines across, and they're lining up that way. And then I need to do the same thing in the vertical direction. So I'm going to press on the button, and then I'm going to change the scaling so that, yeah, there we go. So now my little dots line up where they're supposed to be. Well, not where they're supposed to be, but they line up on a grid now, which I think is much nicer. Now, remember when we took a look at the signals, it was also a clock signal, and the data is only sampled when that clock is valid. And what we're showing here is everything. There's no gating of the clock, okay? Well, we can sort of do gating of the clock by going into XYZ mode. What is that? Well, it's X and Y mode with Z as the intensity. But the Z channel, the third channel here on our scope, is going to be the trigger, the clock, right? So when the clock is high, we're going to display the very brightest display. And when the clock is low, we're going to display the very dimmest display. So if we turn on XY mode, you see everything gets very, 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 very quiet. And hopefully you can see that on the screen there. It did get awfully dim here. So I'm going to turn up the intensity by changing the by changing the Z knob here. I think that's about as bright as it gets. But you can see we're getting an awfully nice looking picture now. So we've done a couple things. First, we've scaled it so that we line up on a grid, and then we've turned on XYZ mode where we gate the information so we're only seeing what we want to see. If we turn off the gating, we kind of get everything, which is fun. But if we just want to take a look at kind of where the data is, that's sort of what's going on. So you can kind of see the jitter of the data, and that's during the clock period. Now remember that the clock is used when the rising edge of that clock is used, not the top level. And what we're showing here is basically the top level of the clock. So it's a little bit hand wavy to do it this way, but it does get you a nicer looking picture. There's no way to just look at data on a rising edge in this particular type of display with this particular instrument. But anyway, I hope that helps. The XY mode, XYZ mode, scaling it, and using the intensity of things.